All right, good afternoon, everybody. I think the mic is not working. Dead battery, or close to dead battery. It's working a little bit. All right, so I'm prepared today. I'm recording audio on the iPad as well, so alas, hopefully we'll end up with full voice coverage throughout the class if everything works okay. Monday, I don't know about you, but I felt like people really wanted us out of this room. Yeah? Was it just me, or did we just all feel a little shoved right out the door? Yeah. Should have left earlier? We should have, I think. People really wanted to be in here, so that was a little awkward, and I'm apologizing now because I was distracted and trying to think about how to get everything covered in the minutes we needed to, so things were disjointed for the last 5 or 10 minutes of class. Today, are you prepared to try to regroup and figure out what's happening with light? Yes. Hopefully this is going to work. So I want to start on this slide. We're going to go from here sort of toward the end of the chapter and then regroup and go back to the start and fill in some gaps. I'm sorry that you kind of have half coverage for what's been going on in lab already this week. Hopefully things will make more sense after I talk about it a little bit as well. So, we briefly mentioned polarization right at the end of class on Monday. Polarization. The reason I want to start here is because it's very much focused on the idea of the electromagnetic wave, which we just learned about at the end of chapter 16. So you can see we get to use this exact same diagram. Yay. Whee. And we have to remember that an electromagnetic wave is varying electric and magnetic fields that are perpendicular to each other. Yeah, it's already gone. Alas. I'm just not going to worry about it. I'll just post the audio file as well today, and that'll be fine. Let's see. So in the idea of polarization, we're going to focus completely on the direction of the electric field and the plane that the electric field is in. So this particular type of electromagnetic wave that we talked about being produced in chapter 16, where we essentially used conductors that were aligned vertically and resulted in electric fields that were vertical. I'll get out of your way. Go right ahead. Gives rise to what we would call a linearly polarized EM wave. The electric field is specifically along a single line or in a single plane. It's produced by what we might call a linear antenna, which was that apparatus we had producing EM waves in the last chapter. To contrast this, it's also possible to have unpolarized light. And you can see the way they've represented unpolarized light with all these little arrows. This is electromagnetic waves that are a mixture of different planes of electric fields. So instead of having something that's really nice and neat where the electric field is all in this one plane, I've got a mixture of all these EM waves where some of them maybe are in one plane and some of them are a little off from that and maybe some are completely backwards. There's a bunch of different planes that the electric field lies in. So first of all, do you see the difference between this particular type that we talked about producing last chapter and maybe regular EM waves that are a mixture of a bunch of different polarizations? Good? Maybe? Okay. So notice here below, unpolarized light. This kind of happens a little more regularly around us. Just light from the light bulbs in this room is unpolarized. The electric field has no preferred orientation. It doesn't all live in a single plane. Okay? So what does all this mean? Before we go to the next slide and start applying this a little bit, let me familiarize you some with sort of the notation that's used, at least the visual notation. Instead of drawing this electric field that's waving over and over again, it's easier to just draw a vector pointing kind of both directions of the electric field. You can see this represented here. So to describe the polarization direction and the plane that the electric field is in, we just take a vector and point it in the positive direction for all the electric fields that are positive and one in the negative direction for all the electric fields that are negative, and just let that be it. So we're sort of simplifying down the full EM wave to just tell us the plane that the electric field is lying in. All right? Now notice, this could be a little different. Maybe our electric field doesn't happen to be so neatly aligned on the z-axis but is off at some angle. That's still linearly polarized. It's just the plane of polarization is just tilted with respect to some axis. Or maybe, we just decided to pick an arbitrary X, Y, and Z direction that didn't happen to align with the electric field direction, okay? Linear polarized EM waves. Everything we talk about going forward is going to be based on that. Your question.
So for unpolarized light, do you still have a magnetic field that's perpendicular for every field?
Yes. So it's a terrible mixture of electric fields and magnetic fields in all directions. Okay? Anyone else? No? We're okay? So let's see how we can create polarized light out of unpolarized light. And we're also going to see how it happens in nature a little bit, and perhaps describe an apparatus that all of you have used at some point in your lives to deal with polarized light, even though maybe you didn't know you were dealing with polarized light at the time. So an apparatus that will polarize light is very, very surprisingly known as a polarizer. Yeah, no one thought too long about that terminology, I don't think. And notice the description here. We're not going to dig too deeply into how we make a material like this or exactly what it looks like. I need you to kind of take this statement with a grain of salt. Think of it as a material that has linear molecules in it that are all sort of in one direction, and all of those linear molecules, well, they're electrically conductive. So if it helps a little bit, maybe, I hesitate to do this. Maybe just imagine a square piece of material. And if we had some sort of like microscopic vision and we could see it, maybe there would be lines of molecules that are sort of sitting like this, with a lot of free electrons that are sort of free to move up and down that linear arrangement of molecules, okay? So it's a very specially designed structure that's going to do something with the electric fields when they pass through. And you can imagine if I have, electrons that are sort of free to move, but they're forced to move up and down, and I send an electric field through there, like it's going to interact with those electrons and something's going to happen, okay? In lab, maybe you've used a polarizer already. Did it look terribly special? No, not at all. Like it's just kind of maybe semi-transparent and maybe it looks a little hazy when you look through it. That's kind of it, okay? That's sort of all you need to know about what a polarizing material is. Now, when I pass light through it, maybe some light is going to pass through. Maybe it'll all pass through, or maybe some of it will be absorbed as it tries to get through. So you could think of this as being either partially or completely transparent, sort of depending on the direction of the electric field as it tries to pass through the polarizer. All of this is going to be based on how the polarization of the incoming light and how it's aligned with respect to the direction of the molecules in the material itself, right? These polarizers' lines of molecules form what we call the transmission axis of the polarizer, okay? So think of the electric field of the EM wave and imagine it has a particular plane that it's in. And then think of the polarizer as having all of these lines of molecules that lie in a particular direction, and think about that plane. The relative difference between those two is going to have some effect on how well the light can pass through the polarizer, okay? So take a look there below. I like this analogy. It's weird, and it's also something I've never really physically done, but I think it helps explain what's going to happen a little bit. If you imagine that we just took a piece of wood and we cut a slit in it like you see, okay, and then passed a string through there and then decided to wave the string up and down, right? If this direction, this plane of polarization of the string, if you want to think about it that way, matches the direction of the slit in the wood, which we might think of as the transmission axis of the polarizer, well, then there's really no interference, and you can imagine like those waves can easily pass right through, okay? So let's add to this. The transmission axis, by analogy, is the direction of the slit, and the polarization of the incoming light is the direction of those electric field lines. If they're in alignment, it just goes straight through. Nothing blocks it. You can imagine if I turn the slit 90 degrees, you can see the wave has a bit of a problem, right? They're now crossed. I try to send the wave through the slit, and it just sort of runs into a wall because the slit doesn't match the direction. And in this case, well, you can see nothing gets through. The wave gets blocked as it tries to pass through. There's also all the options in between. It could be perfectly aligned or perfectly unaligned or some angle in between, which is going to allow some of it to get through. You could think of it as like a component of the wave gets through, but not all of it is allowed to pass. Okay? Are we still good? Yes. The amplitude of the wave? Not that I can think of. No. It would here, but like the analogy kind of falls short. Yeah.
Is this whether it's able to pass because it's in the same direction, or if it's because there's why is there a hole in the middle of that?
Why is there a hole in the middle of the wood?
Yeah.
The hole in the middle of the wood represents, if you want to think of it like the gap in between the linear molecules in the polarizing material, roughly speaking.
So then from A to B, how did that, like the linearity, like how did it exactly change to make it not able to make that wave?
So all we did is like physically rotate the piece of wood. Physically rotating the piece of wood means that when this wave gets to this point, it's not free to wave in this direction because there's something physical blocking it there. That's sort of a macroscopic example of what's happening microscopically in the polarizer. There's something physically blocking the electric field from getting through when the transmission axis is perpendicular to the electric field. Yes?
Why do they show the string like still going through? Like if the light gets like completely blocked,
Mm-hmm.
there it's just no light out.
Yeah, well, the string is there, but is there a wave on the other side? There is no wave. Just the thing that's carrying the wave is still passing through. So if you want to think by analogy with light passing in a vacuum, there's still vacuum on both sides. That's what the light is passing through, but the wave of the light is no longer on the other side. Okay? In the back.
This is light.
Yeah.
The magnetic field.
If this is light, the magnetic field is going to be perpendicular to that. So at this angle, I can't really draw it, but you get the idea that it's perpendicular to those waves. Okay? The electric and magnetic field are always going to be perpendicular to each other. Good questions. Anything else? No. So, what happens sort of mathematically when we pass it through? You saw your hand there at the end. What's that?
Is the mic on?
It's not, but I'm recording here. So I'm going to have to email someone to say, need a replacement. This thing's just broken and dead at this point. Alas. So here we have a more simplified schematic once again. We're just getting rid of the whole electric field thing, and we're using this notation to indicate the plane in which the electric field lies. Don't forget that there's all of these varying amplitudes of electric fields, and there's all these varying amplitudes of magnetic fields that are there as well. We're just choosing to ignore them at this point so we can look at this particular application. So we've got vertically polarized light, and then we're going to put a polarizer in the way that has an alignment of its molecules that's off at some angle. There's an angle theta difference between the vertically polarized light and the transmission axis of the polarizer. What happens when the light tries to pass through is two different things that you see represented here and here. First of all, since there's a misalignment, the intensity of the light is going to change. Not all of it is going to make its way through. Because it's also not perpendicular, it's not going to drop the intensity to zero. It's not all going to be blocked, but it is going to block some, okay? The second thing that's going to happen is now the polarization of the light is going to switch to match the polarization of the polarizer's transmission axis, okay? Don't dig into that too deeply. I'm hoping that you can sort of, I don't know, conceptually see why that might be so, all right? If you imagine that even the vertically polarized light could be split into two components, one of those components matching the direction of the polarizer, it's only that component that can get through, which leaves me with polarized light in that direction. There's just less of it because one component is now gone, okay? So notice, this equation tells us how much gets through. So if I naught is the original intensity of the light, what we're left with is I naught cosine squared theta. This is known as the law of malice. That just sounds terrible, doesn't it? So we could say I is equal to I naught cosine squared theta. I feel like sounds Klingon or something to me, you know? It's like, we must obey the law of malice. It's just what it feels like. That's the end of the story there, law of malice. So if you start with polarized light, send it through a polarizer, this equation gives us the new intensity of the light. Your question?
Is it always like that? Is only one part of the component, like only one component passes through? Like, is it always that component that's equal?
It is always the component that matches the polarizer. I'm trying to decide if I can draw something here that helps, but everything is at a weird askewed angle that's going to confuse things.
Components like X and Y component, but this is like a different kind of.
Yeah, instead of X and Y, it's like parallel to the polarizer and perpendicular to the polarizer. So you might, I don't know, you could maybe draw something that looks like this. This is one component, and this is another component, and it adds to give me the original. This one is getting blocked because it's perpendicular to the direction of the polarizer. Okay? Yes?
So if the incoming light is already polarized, how does it have multiple components?
Because I can split anything into components. Just because it matches like a y-axis. In this class and the previous class, we always dealt with components like in an x and y direction, but I can have any arbitrary perpendicular axes, and I can define components any way I want to. Okay. In the back. Why is there a cosine squared? Oh, I haven't looked at that derivation in a while. I don't remember off the top of my head. Did anybody read that part of the textbook? No, you didn't, did you? Yeah, I don't remember off the top of my head. I'll have to leave that to you to look it up. I think we're good here, okay? This is polarized light passing through a polarizer. What happens if we start with unpolarized light? We've got crazy light in all directions. Not crazy light in all directions, crazy electric field in all directions. And now it passes through the polarizer. You might imagine that once again, a bunch of light is going to get blocked, so it is going to change the intensity of the light. Anything that's perpendicular to the transmission axis will be blocked perfectly. Anything that has a component that's perpendicular to the transmission axis will be blocked as well. So a lot of different parts of this light are going to get blocked, and you're going to end up with only light that's polarized in the direction of the transmission axis of the polarizer. And you can see this time, it just so happens to work out that the intensity gets cut in half. That derivation I don't remember either, and we're not going to worry about it so much, okay? I don't think either of them are hard, so if you want to look them up, like maybe a quick paragraph of work will get you to those. So we could say that the new intensity is just the original intensity divided by 2 if we start with unpolarized light. Okay? That's kind of the end of the math you have to worry about with polarization. If you can get the concepts of these waves that you can't see and understand directions of electric fields, and just remember the rules of what's happening, you can sort of get through all of the problems. I do want to talk about a couple of different things. This one we might save till later, so I'm not going to cross it out yet. I haven't decided if we're going to cover it in this class yet. Instead, I want to talk about another way that light can be polarized. We can potentially use polarizers, like custom-built things that polarize light, or it simply happens in nature all the time because you've probably used polarized sunglasses that are using this idea to sort of block certain reflections that can happen, okay? So, first of all, I love the drawings of these people. Wow. Is this the same dude that was on any of our other slides that you remember? Remember was that last semester? No, that was earlier this semester, the guy in the white t-shirt and the blue pants. Is that him? Yeah. Different hair? He's also at a slightly different angle, so it's kind of hard to tell because we had 3 different dudes, if I remember correctly, in one set of slides. I don't know, maybe this is a 4th one. This guy is clearly upset at what he's seen because apparently there's a death ray from the sun that's striking them in the face. Like, I don't know what's happening, all right? Instead, light from the sun is unpolarized, which you see represented here. However, once it reflects, some of the components disappear, or they actually transmit into the water or into the surface that it's reflecting off of, leaving polarized light. One way to think about this, and this was in your textbook, and I thought it was a particularly helpful example, is just to imagine this unpolarized light with all of these arrows pointing different directions coming down on the surface. Anything that has a vertical component or even has a partial vertical component that's pointing into the water gets stuck. Right? So, right, arrows that are pointing down, like they try to hit the water and they're like, they don't bounce off. It's only the horizontal components that can bounce because, well, they don't have sharp arrows pointing down. It's kind of bad, but it helps you remember what's going to happen, okay? So all of the components that point into the water don't reflect. Instead, they transmit into the water or maybe just stay there completely. And you end up with horizontally polarized light that's reflected off the surface and into your eyes, okay? So the thing is, what you see here is essentially what? Like, big bright spot, right, from the sun. Now, that's not terribly helpful. Or maybe if you're driving down the road, right, and there's like some huge bright spot that maybe we associate with glare, which is really just a reflection off the road. It causes problems. You would like to block that. Polarized sunglasses allow that to happen by having a transmission axis that can block horizontally polarized light. So which direction is the transmission axis of polarized sunglasses?
Vertical.
Exactly. They must be vertical. So for sunglasses, must be vertically polarized to work at all. So the next time you see a big bright reflection that is, bothering you, put on some vertically polarized sunglasses, but then see what happens if you rotate them 90 degrees. They're probably not going to work so well anymore, so not terribly helpful. But alas, you can kind of see how things are working. There is a rule for this, if I can find it. Here it is, okay. Something known as Brewster's angle. This whole chapter is just weird. Brewster's angle. We could say this is the incident angle. Well, incident and reflected because they have to be equal. Remember the law of reflection? Yeah. Incident or reflected angle at which the reflected light is totally polarized. So it's kind of the ideal case, which is really what's being described up above, the ideal case where we have complete polarization as opposed to maybe something that's tending toward one particular direction. Brewster's angle. How do we calculate Brewster's angle? Brewster's angle is theta sub b for Brewster. And we have to put a tangent in front of it. And it's equal to N2 over N1, where we could say this is, maybe it would be better if we call that I and this T. I don't know if that helps. So this would be the index of refraction of the air, and NT would be down in the water. There's no way to draw that. The index of refraction of the stuff that the light is reflecting off of. Here it's water, maybe it's the road, maybe it's something else. Tan of theta b equals nt over ni. That is the angle of reflected light that gives you total polarization. And for now, that's the end of polarization, okay?